Okay, so we continue our discussion on complexity classes, and in this lecture we're going to talk about quantum complexity classes. So, as we mentioned in the previous video, a complexity class is an equivalence class which contains all sets or all problems that have the same amount of algorithmic complexity, okay, time complexity wise or space complexity wise, okay. Obviously, we are interested in only decidable problems, so it's a metric that is defined within the decidable class. So we already mentioned about the class P and NP. P is defined as a set of all problems solvable by deterministic Turing machines in polynomial time, and NP is a set of all problems solvable by non-deterministic Turing machine in polynomial time. Um, the exact relationship between P and NP is unknown, and it's an open problem, famous in mathematics and computer science. We know that P is a subset of NP, but we don't know if the other direction holds. So there are a couple of more complexity classes concerning probabilistic Turing machines. In order to understand the complexity classes of quantum Turing machines, I think it's better to mention the complexity classes for um, probabilistic Turing machines. So the first class is called BPP, also known as bounded error probability polynomial time. So this is the set of all problems solvable by probabilistic Turing machines in polynomial time, with the possibility of some errors. Okay, so to be more precise, if M is a probabilistic Turing machine and that decides some language in BPP, and if X is an input, then M accepts X with probability at least 1 over 2 if X is an L. Otherwise, M rejects X with probability um, at least 1 over 2, okay, or greater than 1 over 2. So this defines the class BPP. One smaller class, which is a subset of BPP, is called RP. RP, I think it's called randomized polynomial time. Randomized polynomial time, this is the set of problems which can be solved by a probabilistic Turing machine in polynomial time with the only possibility of giving false positives. Okay, so false positives means that the machine can accept the input even if that string does not belong to the language. Okay, so to be more precise, we say that if M is a probabilistic Turing machine that decides some language L in RP, and if X is a string, then M accepts X with probability at least greater than 1 over 2 whenever X is in L. But M rejects X. It rejects X with probability 1 if X is not in L. Okay, so we only allow false positives here. We don't allow false negatives. I mean, if the string is not in L, then the machine is certain to reject that input. Another class is called ZPP. which stands for zero error probability polynomial time. So this is the class of problems that are solvable by a probabilistic Turing machine in polynomial time with zero error. Okay, zero error means that if M is a probabilistic Turing machine that decides some language L in ZPP, and if X is an input, then there's less than a 50 chance and 1/2 chance that the machine will give I do not know state. Okay, but if the machine does know that X is in L, then M accepts X with probability 1, and it rejects X with probability 1 as well if X is not in L. Okay, so the machine could go into I don't know state with probability less than 1/2. But other than that, it will decide whether or not the string is in L or not with probability 1. Alright, so remember that how we defined the complements. We could also talk about the complement of RP. And apparently, we could write this as a theorem. The intersection of co-RP and RP is equal to ZPP. Okay, and another theorem is that any problem that is in BPP is also in P space. So BPP is a subset of B space. Okay, so now we can define the quantum counterparts of these classes. Okay, and they're defined exactly in the same manner, except that instead of using probabilistic Turing machines, we use quantum Turing machines. The class BQP is called bounded error quantum polynomial time. This is the quantum counterpart of BPP. Okay, so quantum version of BPP. The class EQP, called exact quantum polynomial time. And this is the quantum counterpart of P. Quantum counterpart of the class P. And we finally have the class ZQP. ZQP means zero error quantum polynomial time. And this is the quantum analog of ZPP, as expected. It's defined exactly in the same way. All right, so note that any probabilistic Turing machine can be simulated by a deterministic Turing machine. Okay, so they're all equal in computational power. So P is indeed a subset of ZPP, and also P is a subset of BPP. What about the relationship between the polynomial time classes and quantum polynomial time classes? The probabilistic classes and quantum classes. We can give this as a theorem. So this is not easy to prove, but you can find the proofs in Gruska's book. The first one says that P is a subset of EQP, which is a subset of BQP. Okay, so this is the first property. And secondly, we have that BPP is a subset of BQP. Okay. And third, finally, we have BQP is a subset of P space. Right. So we can give the overall picture by the following hierarchy. Okay, so I'm going to draw a hierarchy of complexity classes. So at the bottom we have P. Well, actually below P we have like log time, but I'm not going to write those. So P is a class of problems that are solvable in polynomial time by deterministic Turing machines. And then above P we have ZPP. Above ZPP we have co-RP. And here we have RP. We also have NP above RP. And we know that P is a subset of NP. Okay. And then above, so co-RP and RP is bounded by BPP. Okay. BPP is bounded by BQP. And below we have, so we know that P is a subset of co-NP. Co-NP. We don't know the relationship between co-NP and NP, so that's why they're not connected in the hierarchy. Okay, let me actually draw co-NP a little bit more above, because co-RP and co-NP are related. So co-NP and yes, co-RP. We also have EQP above P. EQP. And we have ZQP above EQP. Above ZQP we have BQP. At the top we have P space. Co-NP is a subset of P space. BQP is a subset of P space. And finally NP is a subset of B space. Okay, so this is the overall picture of the complexity classes, including both deterministic and probabilistic and quantum complexity classes. A natural question that we can ask whether or not non-deterministic computations have any advantage over deterministic computations in terms of space complexity. Okay, and the answer is negative. Okay, non-deterministic computations don't have any advantage, or at least they don't have any serious advantage over deterministic computations in terms of space complexity, because Savage's theorem tells us that Savage's theorem, and it goes like this. It says for any function fn greater than or equal to n, okay, for some n, NP space, so this is the set of problems that are solvable by non-deterministic Turing machines in polynomial space. NP space Fn is a subset of P space Fn squared. Okay, so in other words, this theorem tells us that if a language is decided by a non-deterministic Turing machine with space complexity in the order of Fn, then we could also decide the same language using a deterministic Turing machine with only quadratic compromise. Okay, so this in turn shows that there is no space complexity analog of P versus NP. Okay, so P versus NP problem only matters in time complexity. Okay, so there is no space complexity analog of a similar problem. Now, the quantum analog of the class NP is a bit more interesting. So this class is called NQP, okay, NQP, and this is the quantum analog of NP, and this was shown to be equivalent to what we call the class CP. Okay, let me first write the statement. So NQP was proven to be equivalent to the class CP, and CP is the class. So this is the class of decision problems that determine whether the number of accepting computable paths of a non-deterministic Turing machine equals that of rejecting paths. So let's write that down. Whether the number of accepting acceptable computations of a non-deterministic Turing machine equals that of rejecting paths. Okay, so this is a counting complexity class. Okay, and one problem that falls into this class is called the graph non-isomorphism problem. So a graph isomorphism problem is to decide, given two graphs, G1 and G2, to decide if G1 and G2 are non-isomorphic. Okay, nothing else. So we just decide whether two given graphs are non-isomorphic. So this problem, the graph isomorphism problem, it's not known to be in NP. Okay, but this is in CP. Okay, and CP is exactly the class NQP. Right, so this is quite interesting. Okay, so these are the essential classes, complexity classes, probabilistic Turing machines and quantum Turing machines, and we also covered deterministic Turing machines and their complexity classes, time and space complexity classes. So this is the end of our lecture series, and thank you for watching.